So diodes, back to diodes. Diodes have three main uses in organ building. The first is rectifying AC current, as we've seen. The second is for steering, like we did with the bridge rectifier. Many times in the organ, we'll want current to go from a contact to a magnet, but not come back the other way. Steering is also called isolation. Older mechanical key relays look something like this, where you have a bunch of contact fingers and a plate that mashes into them and sends current to them, either under the key contacts or in a relay in the organ. The separate fingers isolate one note from another. These could be couplers, they could be magnets on a unit action. You can do the same thing with a bunch of diodes here. Yes, one simple switch energizes a bus bar. The diodes send the current shooting out that way to keep it from coming back in. So if this were connected to a magnet, and that magnet would be fired from some other source, the electricity couldn't go back and fire all these other things. The third application for diodes is spark suppression. And this is probably the least understood but the most fun to talk about. Many of us have gotten shocks from the sparking that can occur at key contacts. Could I just ask how many have felt this? Oh, very, very good. There was this old lady organist in Milwaukee that substituted, and this console had bare contacts right underneath. And one day she got her finger across, Rick?
Oh, thanks.
Got her finger across the contacts on the general cancel. And she pushed, and she screamed, and she dashed off the bench as fast as an 80-year-old lady can dash. And said, "The organ bit me! It bit me! The damn thing bit me!" And indeed, it feels like that. So, in this circuit, current flows from the battery, plus, through the switch, through the magnet, and back to the battery. The magnet consists, as we said, of a mile of fine wire wrapped around a soft iron core. When DC passes through the coil, the iron gets magnetized, and all of its little molecules get arranged very tidily north and south. Energy is actually stored in that iron when you've turned the magnet on. When the flow of current is stopped, as by opening the switch, the energy has to go somewhere. The magnetic field collapses through the windings of the coil, generating a voltage in them. It's the same principle as the generator, except here the magnetic field is moving and the coil is stationary. You remember in a generator we have a magnetic field and we're twirling coils around in it. Okay, so I heard people say, well, the magnets become a generator. Well, how can that be? What happens to the electricity it's making? Well, when you get that shock, when you got that shock, the energy was turned into four-letter word energy. If your finger hadn't been there across here when the switch was opened, the voltage would have built up across the terminals of the switch to a point where it was high enough, maybe 300, 400 volts, to jump the gap and cause a spark. When the voltage gets high enough, the air gap is no longer a good enough insulator to prevent the current from jumping across. Contact burning was the single major cause of unreliability and failure in early electric actions. Every time a key was played and released, a little blue spark vaporized tiny amounts of bronze or silver contact material. This was no problem. Actually, it was advantageous because it left relatively clean metal behind for the next time you played it. However, eventually, of course, the contacts would fall off, and that was that. So, it was known this problem was known early on, and in fact, someone showed me an E.M. Skinner woodcap magnet that, in addition to its normal winding, had
It's up there, right?
It's up here, of course it is. Oh, good. Okay, current is going this way, right? From plus to minus. It's going through the magnet, this is plus and this is minus. The magnetic field is built up. You open the switch, the magnetic field collapses through the windings, and I like to think of it in terms of inertia. We've got billions and billions of electrons going hell-bent for election around this circuit. And you open the switch and they say, what the? They want to keep going. And so they all build up here. Big negative charge. And there's power in numbers to get enough of them there. The voltage goes high enough that they spark across the open switch. And everything relaxes back to normal until the next time you play the note. So, how can we get rid of the energy so it doesn't damage the switch contacts? Well, Mr. Skinner had a solution, and this wood cap magnet that I saw, and not on all of them, he added a second winding of resistance wire. That's that wire that doesn't conduct very well, like this. Well, actually there, okay? Excuse me, so when you close the switch, current now goes two places. It's a parallel circuit. It goes through the magnet and it goes through the resistor. So this is hopefully doing productive work. The resistor is just wasting electricity. But it comes into play when you open the switch. So think about it. The electrons are going here and they want to get back to here. So what's the path of least resistance? Oh, that's cool, resistance. Yeah, the easiest way. They're going through here, and they go through the resistor and back. So instead of building up the switch, they simply go through the resistor. Okay? Is that clear? It works, and but it wastes electricity. So, there's a more modern way of doing this. Instead of the resistor, we put in a diode. Like so. Okay? So the diode is connected along with the coil of the magnet. Plus comes up here. It sees the diode and says, no, I'm not going there. Goes through the coil, and the circuit works as it did before. The magic happens when you open the switch. Okay, current is going this way. Now, where shall we go? We can go uphill this way, it's a lot of work, or we can just go through the diode. And it does. And that energy is dissipated through the diode. And the sparking here goes away. After we finish, at the last bit of this dog and pony show, has the oscilloscope connected across the magnet, and we can actually see that huge spike of hundreds of volts and what happens when you put the diode in there. Okay. I think we're done with that. Before we get further into that, we understand what a diode is. It's two pieces of silicone, a positive doped and a negative doped kind. A transistor is simply basically two diodes back to back. So we have an N-type silicone thing here. We have a very thin layer with the wire coming out. And we have positive here. Think of it like a bologna sandwich. The silicone is the white bread, and the thin layer in the middle is the control circuit. And the way a transistor works is current will not flow from plus to minus unless it's allowed to flow out the base. Think of it as getting the thing going. So if we allow current to flow through here and out here, current will flow through here and out there. The advantage of it is it takes only a small amount of current to turn the transistor on, and the transistor is then, like a diode, able to carry lots of current. from milliamps to amps to hundreds or even thousands of amps, which is very useful in the organ because we are interested in turning large electromagnetic loads like slider solenoids on and off, but we don't want to have to do it with knife switches. So a transistor is really quite ideal for organ building. It's found in the rest of the world as, for example, in audio amplifiers, because a transistor, like a water faucet, doesn't have to be completely off or completely on. You can open and close it, and if we had this transistor driving a loudspeaker, for example, it could make the speaker move or relax and do it very quickly and produce sound. Transistors can also act like leaky water faucets when they become, and that's the term, leaky. If something damages them and punches holes through the base layer, current can flow even when it's off. And if this transistor were switching magnet in an organ, the symptom of its being leaky might be that you play the note and release it and it stays on. And you put your trusty meter, like one of them that's circulating, on the magnet, and you see when it's on it's 12 volts, when it's off it's like 3.5 volts. Where did that come from? Well, it came from the damaged transistor. So any electronic circuits that use transistors for switching pipe organ magnets need to have that same sort of suppression diode that we drew to quench that energy, to get rid of it so it can't do any harm. Obviously, it's not going to spark across a key contact in a solid-state relay because there's lots of shit in between the key contact and the magnet. But that energy can easily damage the transistor. Questions about any of this? Wait till after lunch. They'll be just dead. Yeah. Okay. This looks like a lewd drawing. Let me assure you it isn't. You can pass that around. It's just sort of a fun visual representation of Ohm's law. It came over the internet, and of course I was immediately going to trash it. But instead I printed it. Okay. So Ohm's law, voltage, current, and resistance. This is simply a meter that's inserted in this circuit. The plus and minus is coming from a little power supply in the back. And if we plug oh dear. Ooh. The hardest thing about this demonstration is finding the holes. Okay. It's upside down. The color code here represents the resistance of the resistor. So the first letter of each one is black is 0, brown is 1, black. Yes, and we have violet, yellow, and orange also. So this is a 100 ohm resistor, and you can see just, approximately how much current it's letting through. Now, let's see, here's one. Here it is. This one is 470 ohms. And you can see it lets less current through. Okay? Here, Rick, is a variable resistor, and I've very cleverly soldered a fixed resistor in it so that if I crank it down to 0, it won't burn out the meter. So we plug this in here, and it says here it's 500 ohms. So, okay, think of it as a sorts on to okay, enough of that. So, any questions about current flow and Ohm's law? No? Great. Throw this one away. same circuit. In this case, instead of a meter, we have a light bulb. And it's meant to demonstrate that the diode is a one-way valve. So the arrow points this way. And if we plug it in here, you have to trust me that the light is on. The light lights. If we plug it in the other way, trust me, it doesn't. The last time I used this thing was at an AIO convention down south. And I had rigged up some magic flash powder in the back, but when we plugged in the diode the wrong way around, there was this great plume of smoke. You can find it on the website, the video of that year. I don't remember which one it was. But
2008.
2008.
Yeah.
Okay. We're not going to do that here. Sorry. Too much fun. Okay. So the diode. Two things specify the diode: the amount of current it can carry without becoming toast, and the amount of voltage it can block and not carry. Oh, this one. Okay. Let's put this poor old resistor here, where it seems a million years ago I made these. These were in my completely anal compulsive phase, and just the right colors. Okay, so positive coming down here. It's going through the resistor, and we can put one of our even more beautiful diodes here. And presto, the light lights up. I mean, there's no rocket science here. When I first heard about diode coupler switching in an organ, I knew that it didn't have 61 contacts. How did it work? How could you add a diode to make something not work? It was a mystery. But this will demonstrate. So the current goes through here, and it goes through here, and through the light bulb. If we give it, and to ground, wants to get from here to here. So if we put another diode in here, the light goes out. And it goes out because the current has a choice. It can go either this way, this way. This way, it has to light up the filament. It has to take that piece of metal and make it white hot glowing. That's a lot of work. So instead, it just simply goes through here to ground. So on, off. Clear? Okay. Fix you sometime. Okay, this is the fun one. And we have to plug in this oscilloscope. Okay, what we have here is basically the circuit we drew there. There is a magnet, which here is a Reasoner, now OSI 601 direct electric valve of 90 ohms. The switch here is actually the contact on an AC relay inside here, which will go on and off 60 times a second. So when I turn it on, you will hear you'll hear the relay going. You'll maybe be able to see the magnet working. It won't go fully open and closed 60 times a second. It'll sort of hover nearly closed. That's this. I know enough not to put my fingers across those contacts. Now, oh, excellent. So, well, I'm not going to write on the oscilloscope with that. That would not be a good idea. Okay. So what you have here is, oh, wow, ugly finger. I'll point over here. This is measuring voltage this way and time this way. So the distance from here to here represents 12 volts, which is the voltage of the power supply that's running the magnet. And this is one cycle, this is 1/60th of a second, and you see it switch on and then switch off. When it switches off, the voltage goes way the hell up there to several hundred volts, and then it tapers off. And what's happening then is the magnetic field is collapsing through the magnet, it generates voltage, and if we were to pry that thing open, we would see little festive blue sparks at the contact of the relay. Is that clear? Does everyone know what you're looking at? Okay, now for the magic. Take a diode, any diode, and if we put it in, it's essentially wired across that magnet, right across the terminals. If we put it in one way, it'll be a short circuit. That would not be good. If we put it in the other way, it's like we drew, and it becomes a spark suppressor. So, I plug one end in here. And when I connect this, we're going to observe two things. You'll see on the scope that huge high voltage spike goes away. And also, the valve, which is now hovering, it's barely even opening at all, will now hover further open because the energy it's producing is being channeled back into it, and it makes it slower to close. So, hopefully this is the right way around. You see what happened? You see the 12 volts at the bottom going on and off. When we take this away, we have the big spark. And if you could look at the magnet, when the diode is in the circuit, the magnet is hovering about a third of the way down from closed to open. So what is, let me do that again.
Oh, Jesus.
I didn't do it this time, guys. I'll try that again. So, in homage to Mr. Skinner, I've not tried this, so I might get that. Oh, well, you can't see it anyway. See, it reduces it. It doesn't eliminate it. Okay, you'll have to trust me on that. Are there any questions about diodes or diodes as spark suppressors or isolators? That's okay, good. We're not going to do it anymore. No questions? So the diode is a one-way valve? Yeah.
Is the spark suppressor also called a flyback?
Yes, indeed.
Okay.
You often used to hear the term flyback in television sets. The front of the picture tube was the anode, and it was about plus 25,000 volts. And that was generated by a flyback transformer. And basically used this principle of magnetic field collapsing. Okay. As we said, transistors are basically two diodes back to back with a control circuit called the base that allows you to switch the diode on or off or anywhere in between. The sort of package that a diode is enclosed in the trade is called the can. You know what the pretty little silver ones here look like? That's called a TO3 can. This demonstration used to be done in England when Henry Willis would say, "Oh, is that a Heinz can?" And I think it probably was. So, believe it or not, inside there is a real transistor. So, we'll plug it in here, and they're very cleverly arranged with leads so that you can't put them in wrong. which is very... Okay, so there's a resistor drawn here, but it's actually in real life going to be that light bulb. So let's take a resistor which is 470 ohms, and we'll plug it in here like so. Oh, and it didn't light. Why didn't it light up?
Because it's already building.
It's never done that before. Oh, there it is. Okay. So what's happening here is positive current is coming through this resistor, limiting it to a relatively small amount. It's coming into the transistor. It's turning the transistor on, which allows enough current to flow through the transistor to light the light bulb, or work the pull-down magnet, or the chest magnet, or whatever. It takes a lot less current to turn it on than the magnet requires to operate. Or here is 820 ohms. Still, if you put this here and tried to light the light bulb with it, nothing would happen. So what it's doing is it's allowing you to use a small amount of current to turn on the transistor, which will then do the heavy lifting of working the light bulb. Okay? Like diodes, transistors have a few specifications. Since when it's off, it has to block the flow of current. It has a maximum usable voltage called the breakdown voltage, above which this becomes effectively a piece of wire. And it also has a spec called NPN or PNP, which identifies the polarity of the device. And it also has another factor called gain, which is how much it will amplify the signal. So you put in a small amount and you get out a lot. The gain may be from 50 to 500 or whatever. Okay? You know, when I started doing this back in the late 70s, it was like black magic and nobody trusted it. You've become an easier audience. Okay. This is the last one, I promise. So what we have here is essentially the same thing. There is a key switch here, which goes through a resistor, limiting the current to a small amount. Then it has a choice of going through a diode to turn on a transistor and work the load, which again is a light bulb. Oh, different light bulb. Or we can make it not work by putting another diode here. So this is where we use up most of the parts on the table. It's there. Stay. Fortunately, manufacturing in the real world is a lot easier. Okay, there's enough so that why doesn't this work? I don't know why it doesn't work. Maybe this resistor is broken. Well, if this were working, what we would do is we would demonstrate that when we turned on the key, current flows through here, through the diode, turns the transistor on, and the light lights up. If we put in a second diode, like the diode switch we saw earlier, here, we would see that if we play the note, if we play the key, it goes on and off. But if we leave it on, and we turn on this switch, which allows the current to go through the stop action diode, the note will go off. Can you all trust me on this? Okay, thank you. So this is the principle of diode switching, which is used by the various manufacturers of these devices. We're seeing less and less diode switching these days in organs because the more flexible computer-based systems have taken over. But still, for very simple applications, a diode may be useful. This is a diode coupling board from solid state. Here are the transistors. There are no spark suppression diodes on here for some reason. Maybe that's why I have this. And each one of these groups of 61 parts corresponds to a coupler switch or a stop switch on a unit organ. The current from the key comes through here. It's limited by this resistor. It goes through one of two diodes. One can sort of snake its way up here and turn on the transistor. The other one punches through the board and goes onto a vertical track here, which, if you're familiar with Pitman chests, this would correspond to the stop action channel, and the one over here to the T channel. Corresponding to the stop action magnet and primary valve on the Pitman chest is this group of parts, which is a stop relay. And it needs to reverse the sense of how things work. If you look at a console, let's say the keys, when you play the key, it sends positive out the wire. When you turn the stop on, it sends positive out the wire. But what we want here on this bus bar, which is the guy running on the back, in order to turn it off, that has to be negative. So we need to invert, because we don't want to have negative switches working backwards on the console. I was going to bring some Peterson boards, but it just got too late last night. No, it wasn't last night. It was the night before last. Isn't it amazing? Time flies. Well, I don't know about you, but I've had fun. And when you all clear out, I'm going to figure out why this thing doesn't work.
Can you know the diode on top?
No, that's the spark suppression diode.
Okay.
Yeah, I should have plugged it in because that's why I have 3 diodes. But it should have worked with just the resistor, one diode, and the transistor. Maybe it was that electrical fault that did it.
Yeah, pull the bulb.
Oh, the bulb.
Yeah.
Whatever. Joe, unless you have the answer.
You have the answer, I'm sure.
Oh.
You talked about the partial transistor failure.
Leaky.
I have that situation in Boston. If the transistor failed completely, it would then be the switch.
It would be dead.
Transistor.
Yeah.
So it would be dead.
Right.
Because I think when you were describing the transistor before, you may have indicated that it would be a short.
Yeah, there are actually 3 states. It can work 4. It can work properly,
Okay,
or it can become shorted and be on all the time.
okay.
It can burn out and become open. If we did the can opener trick here, you would see that on the floor of the transistor, there's a little tiny chip of silicone mounted. And it has 2 very, very fine wires, the size of gray old hairs, going from the chip to a lead and the chip to a lead, and then the base itself to which the transistor is attached is the 3rd wire. So when it goes open from overload, typically what happens is that little wire will make like a fuse and it's gone, so it's dead. I used to cut them open and try to solder new wire on, but it didn't work. That's a joke. Close your mouth. So it can go short, it can go open, or it can go leaky, which is partially on. And that was what we were talking about. Ryan.
To further confuse matters, there's an organ I take care of where the builder, who was an amateur builder, decided to use the opposite type of transistor, whereby you had to supply current to it to keep the circuit off.
Mm-hmm.
Any idea why that guy would have chosen to do that?
Electronics engineers sometimes do that. In fact, I was working at SSL when they put out their first multi-level combination action. And that system receives positive from the stop key on the console. And it regurgitates it and sends it out positive to the organ. The reason it passes through there is so that it can provide things like ventals, which shut off the stop action, crescendo, which turns it on, sforzando, which turns it on, so it has control of the stop action. The engineer thought it would be very tidy to use NPN transistors there to send out plus to the organ. But he realized that in the way he had drawn them, the computer would actually have to turn them off. But that's okay, it only took like 3 seconds to come on. Yes, of course, it's so obvious. So yeah, there have been occasions where people have done that. A NPN transistor historically is cheaper than a PNP, and that may have been part of the reason, but it's silly. There's lots of silliness that goes on. Shall we talk about power supplies a little more? There's an Astron sitting right here, inviting comment. And I thought I was done with this. The very simplest brute force power supplies consisted of, let's be blue. We've drawn this before. It consists of a transformer with lots of windings, 120 volts here, big heavy iron core, 15 volts here, and it goes through a bridge rectifier, which you'll have to trust me comes out plus and minus. And that goes out here. Then other parts you might find if you open that steel carton would be a capacitor, which we didn't talk about. A capacitor is like a winker in a wind system. It consists of 2 pieces of metal separated by a thin, it's called a dielectric, it's an insulator. And so a simple tubular capacitor from those marvelous old radios I trashed would consist of 2 pieces of aluminum foil with some wax paper in between, and they'd be rolled up, and the lead on one end goes to one of the aluminum foil layers and that to the other. So that when you, in this case, let's just arbitrarily say this is plus and this is minus. If at this point, the negative electrons will all build up here, the capacitor, and they'll push the electrons from the other side away, and it'll be a stable condition. But since the voltage coming out of here looks like this, what this guy will do is just exactly what you would do with a winker in a wind system. You want to get rid of the wiggly wind, unless you're selling that as a feature. So you put in the capacitor, and that will make it sort of something like that, much better. The next bit of refinement that can be done here is putting what's called a choke in here. It's a very good term for it. It's like a transformer, but with only one winding. Transformers have what the engineering buffs call reluctance. I know, I've got a lot of reluctance. I face it every morning when I look at my desk. It's resistance to change. So when the current goes through this choke coil, it tends to want to keep going the way it is. And if the bridge rectifier or the electrical god messes up the power for a moment, it will be very slow to change. So it's sort of like a slow moving valve. So that's brute force rectifiers. They're very reliable. The oldest ones you may encounter, instead of having rectifier diodes on metal plates or in a package, had selenium rectifiers, which look like this. They look just like metal plates, sort of like the... England is the only country in the world that has warm beer and cold toast. And they have these devices at the breakfast table that let you put your toast in so they cool off. They say, oh, keeps it crisp, makes it cold. Anyway, you'll look in some of these old rectifiers and see a selenium rectifier like this, which is a metal plate that has a film of selenium on it, as right to the next one, and so forth. And it's a rectifier. It changes AC to DC, but they tend to fail over the years. They start becoming leaky. So instead of the current only going that way, a little bit of it comes back this way. And you could put your meter on it and read a certain amount of AC voltage, like 1 volt, 2 volts, 3 volts, etc. The next bit of evolution comes here. What you have in the Astron is a hernia. You have a big ass transformer that is taking the 120 volts in and converting it to about 30 or 35 volts AC. It then goes through rectifier diodes down in the bowels, which produces 30-some volts DC, which charges up a big capacitor here, which filters it. So now we have semi-lumpy DC at about 30 volts. We don't want that in the organ. We want, let's say, 12 volts to come out here. So the 30 volts goes through the black magic card here, which has a bunch of parts on the back. It's called a voltage regulator card. And it controls the 4 big power transistors here, which are like the water faucets. It takes the 30 volts and it limits it down. They're constantly opening and closing depending on the load of the organ. And the goal is to keep this at a steady 12 volts, regardless of how much current you draw, within the range of the unit. If you have more than one of these in parallel, there's this little red binding post here, which goes to, what goes on here? It actually allows the voltage regulator cards from one rectifier to talk to another and kind of keep them in pace. You can buy these things with knobs on the front for voltage adjustment and current limiting. Don't, because someone will turn the knobs and your phone will ring. There is a pot right under here that you can turn to adjust adjust the volume, same thing, adjust the voltage. And you can usually get up to, I don't know, maybe 16 or 17 volts without changing any components on the other side. But you can, if you want a higher range, you can change some components and get like maybe 20 volts out. If you've got one of those organs with wire that's way too small or for some other reason you need that much. It's also useful if you're driving, let's say for example here are straw knobs on a console that are rated 12 to 14 volts. They're much happier on about 11 volts. They just move very quietly, even more quietly. So you can get in there and tweak that. And then the next stage in evolution is the switch mode power supplies that we alluded to. Okay, your turn. Joe.
Again, I'll ask all the questions.
Good.
The you touched earlier on inrush current limiting, and I know you have advised me on that over the years. Do you want to just explain again how you would do that?
If you order an Astron with a I hate that moment. File not found. It's a little disc. It's a thermistor. It is a device that will pass. It'll pass electric current, but as when the voltage is high, it has a direct relationship, corresponding relationship between the voltage and the current. So when the voltage is high, its resistance will be high, and it effectively makes the thing start up softly. It's wired simply on the input to the power transformer here. And the Astron charges $5 for it. It's $5 well spent. It's another possible course for a problem because, you know, it is in series with the transformer. If it blows, you're all done. Any less complicated questions?
Do capacitors store energy?
Yes,
It keeps it in there and it can hurt you if you touch it the wrong way.
Depends on the voltage. My colleague Vladimir insists on putting a resistor, 1,000 ohms or so, right across this plus and minus, so that without it, this, I don't know if I could take a piece of metal, there may even be voltage in there right now from the last time it was switched on. But if you turn it off and you're in there working and doing something, and you happen to get your screwdriver across there, there'll be a big ass spark. I mean, it's a beautiful thing. Vladdy and I have this discussion. Okay, it's an argument about whether or not to do this. Vladdy, you don't need that. Oh, you need. So he wins and put it on there. So that avoids the problem of you're being surprised by the voltage stored. It's also a good party trick to fire one up and run around with people, wire it up to the toilet seat, or whatever. You're raising your hand, Phil.
In the discussion of power supplies, one of the things that was pointed out to me years ago is the discussion of old supplies versus the newer ones. And I've had discussions with a number of you all about noise on the system, and that some of the power supplies are noisy and some are supposed to be silent. In an electrical term, can you elaborate on that just a little bit?
Yeah, we were talking about the selenium rectifier stack, that as it ages will become it'll become a leaky one-way valve. And you'll get some AC on the DC. That can be referred to as noise. Or you can have more complex electrical noise come through from maybe, I had one once. Big organ, the organist complained that every once in a while stops would move on their own. And I changed boards and I did the incantations and all that still happened. Until one day he said, oh, could you replace the pedal board light? It's failing. It was a fluorescent light, and whoever had installed it had joined the wires with wire nuts, but they hadn't stripped the wires. What? I said. So, they were sort of making contact most of the time, but every once in a while they didn't, and the light went zzz, and the knobs moved. And so that was it. That was a perfect example of electrical noise making it through the power supply, which was an Astron in that case. But it doesn't matter, it can get through all kinds of stuff. The switch mode power supplies are very good at controlling what comes out of the terminals. There's so much garbage there that noise has to go through, and it's got capacitors and other devices that filter it out. It's very unlikely you'll get noise coming out of one of those. The other kind of noise is the buzzing, and it used to be, here, you see that piece of cork right here? That's there because the laminations and the windings aren't perfectly tight on this. They dip it in a vat of varnish, kind of like when you go to the Dairy Queen and you order chocolate covering on your you do that. But it's not perfect, and so they wedge in a piece of organ building cork here to keep it quiet. I had said we'd allow a lot of time for questions.
I had a question about,
Yeah.
for people that don't understand what the sine wave is, the one sine wave that you show going plus and minus is what happens 60 times a second.
Mhm.
And that's why you showed a magnet moving 60 times a second, so that it would show up as one
Yeah,
measurement.
This thing was made in England many years ago, and they have 50 cycle electricity, so the pitch is a little lower, and it's the same thing. The if you were to put the oscilloscope on the electrical outlet there, what you see, there's a ground prong at the top, and then there's a broad blade, which is the neutral. Those both go via separate wires to the circuit breaker panel, and they connect to a bus bar, which is the ground, the earth ground. The small one there, if it's simply a vertical straight line, that means it's a 15 amp circuit. If it looks like that, it's a 20 amp circuit, or if the second blade is just horizontal. That means that it'll have 12 gauge wire going to the circuit breaker panel, which will have a 20 amp breaker. If we put the oscilloscope between those two blades, the neutral and what we call the hot one, you would see the picture we drew of the voltage starting at 0, and it goes up to 180, how many volts? 183, we'll call it 183 volts. It goes up, and then it slowly comes down to 0, and then it goes to a negative 183. The reason it's not 110 or 117 or 120 or any of these monikers we use is that the energy is represented by the area under the curve. And I remember this. It's the only thing I remember from calculus because it was an 8 a.m. class and I didn't do well in it. But if you take these humps and you squish them down, sort of like the fat lady putting on the corset, and you kind of even it all out, you'll end up with 115 volts or so. So it has to go up to 180 some to have the extra energy to fill in the gaps between the humps on the camel's back. Yeah.
Can you or somebody speak about replacing Reisner switches with the little solid state units that OSI sells?
I think you're talking about relays rather than switches.
Yes.
So the Reisner relay has a bunch of the fingers that we draw in there and a chopper plate that comes up. It's drawn up by a horseshoe magnet. I did some tests on those in the early days of multiplex systems, and they tend to operate at about 14 milliseconds. In fact, to have fun, I wired a dozen in a row, so this one turned on, this one turned on, and like that. I thought, yeah, crap, we're trying to put music through these things. Not terribly responsive. So a couple of suppliers have built direct solid-state replacements, which are simply a beefy transistor that turns on a bus bar that has diodes going off to the individual terminals. And you can get them in 4 different polarities, plus or minus in, and plus or minus out to suit the application. The only thing you have, have to be careful about is drawing so much current through the transistor that it heats up, because on the ones I'm familiar with, there isn't a heat sink to get rid of it. But if you're just playing normally, it should work just fine. The answer is yes.
So what I hear you saying is that if you play eighth notes, you're fine, but if you play tied whole notes, it's going to burn up.
Well, it depends. It depends on what you're running with it. If you're running 7 slider chests with pull-down magnets, yes, you may have to restrict yourself to 16th notes, or put a block on there, or use a different device. But you just have to remember that in the Reisner relay, each finger is a separate circuit supplied by a chopper, and the relay doesn't really care how much current you're taking in aggregate from all of them, except it has that nice little braided wire. That would look really good, cherry hot and melting sometimes. One more? We're out of time.
We're out of time? No, 12. Doesn't it say 12?
Well,
Oh, we go till 12?
Yeah.
Here it is, this is where I.
Fine, we can talk about,
stretch.
I'll just talk more slowly. We talked about the Astron connecting a wire from the negative bolt here to the case. And that, there's a little hole here that says chassis. It must be a French word. And then there is the round symbol that, oh, I won't do that, I get confused. I also get rude. So there's a little black wire that goes from that bolt to in here, and I see it's been cut here. I know maybe your guys just cut it, for not being embarrassed before they came in here. But that's what you have to do with these. And this is the 50 amp unit. There's a 70 amp unit that looks just the same, has the same link wire, but it has a fan on the back. You don't have to be afraid of. I've never, ever, ever seen that fan come on. There are somewhere in here 2 devices that are temperature sensitive through which the current of the transformer passes. One of them, when it reaches a certain temperature, will turn on that fan. And the other one, which is rated at a higher temperature, will shut the transformer off. But otherwise, they look the same inside, and the evil black wire is in the same place. The smaller Astrons, you may have to look for the wire, but I assure you it's there.
And you're cutting that so you can put them in parallel.
No, you're cutting it just because that's the right thing to do.
Oh, okay.
Yeah. No.
Well,
You're
then
cutting
we
it-
definitely cut that on purpose.
Definitely.
Yeah.
If you don't, this negative terminal, which is negative throughout the organ, is connected through this wire to the chassis, which is connected to the 3rd prong of the power cord. So you've earthed the organ negative.
Right.
You want this to be the organ negative, not the negative of the whole world and your neighbors and the other fundamentalist church down the road. You don't want them sharing your negative. It can, seriously though, it can get you into trouble.
So I have a question then.
Yeah.
When would you not cut that? What application is that Astron for where it would use that wire you're cutting out?
My understanding is that there are some industries that spec the negative of the power supply to be bonded to earth, to connected to earth ground. Astron told me that that was the case in the Canadian telephone industry, which is why they do it. Bob, do you know of any other instances where?
And even for the Canadian telephone industry, since everything's negative 48 volts.
Yeah, well, it goes from there down, so this becomes
Right.
what we would think of as positive.
Yeah.
Yeah, you just kind of turn it. I worked on a Ruffati organ once that had 4 different voltages, and they didn't all come off the 0. It wasn't like here, 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 and down here. It was up here, and then another power supply came from here down. And it was, I actually had more hair then when I was trying to figure it out. That was a good question.
Thank you.
Sorry the answer didn't meet up.
That's good.
So in a practical application of a magnet, the reason you put a diode on, so in early direct electric organs, a magnet behaved a certain way, and then you put a diode on it would behave a different way.
Perfect. The reason that when the diode was put across the direct electric magnet and it changed its position, it became more open, is that the diode channels that energy back through the coil. And that tends to make the magnet go off more slowly. If you're putting diodes on a Wix organ, bless you, it's a very good thing. The magnets won't bounce as much. The bounce happens when the current shuts off, the valve is open, and the mass in the armature gets moving. The valve slaps against the toe board and goes like that. You've all heard this? It's not a pretty sound. It's like the buzz of fluorescent lights that you switch off and say, oh, that's good. If you put diodes on magnets like this, the organ will sound better. It's a very annoying thing. And what it's doing is it's making the magnets close more slowly. It's a good thing on a direct electric magnet. If you put it on a wood cap magnet on an EM Skinner organ, which is a very sensitive device, the exhaust port is only, that big. And it will slow down the return of the armature, and the organ will feel sluggish. If you put it on a pallet pull-down magnet, a big beefy thing with lots of iron that will pull a pallet on the slider chest open, it won't repeat for nothing. I mean, it really ruins the action. So you need to protect contacts, and you certainly need to protect transistors that are switching these magnets. So if you cannot tolerate a simple, ordinary suppression diode, which, as we saw on the scope, does a perfect job of getting rid of the spike, there are a couple other alternatives. We were talking about transistors having a breakdown voltage. You can put a device across the magnet that will allow the voltage to go up maybe only to 25 volts. And if the transistor has a breakdown voltage of 50 or more, it should be fine. There are two kinds of devices that do this. One is a little flat pancake device that looks like the varistor we were talking about in here. And it's a resistor that changes its resistance as a function of voltage. So when it sees the voltage go way up, it clamps. And so it goes up and off and then down. That's a way of protection. Laukov used to sell all of their heavy pull-down magnets with one of those varistors fitted. Nowadays, they put in a thing that looks like a defective diode. It's a black diode with no band on it. It's like, there must have been this sadist in the diode factory that didn't put the bands on to confuse people. But no, it's in fact called a double diode. It's actually two diodes back to back, kind of similar to a transistor. But it's a spark suppressor that doesn't care what the polarity is. And they put it on as standard because if you're running it off directly from contacts, as foolish as that may seem, but there's still some Europeans that do that, it'll limit the sparking of the contact. If you're driving it with a transistor, it'll keep it from burning up. The other way of doing it is to take, I'll be more careful next time, the non-existent spark suppression diodes that should live here, and running them through a large Zener diode. It's made for this purpose as a spark suppressor. It's like an ordinary diode, but going in the reverse direction, it will conduct at or above a certain voltage. So if you wire it to all the sparks, and let's say it's a 20 volt one, it will cause all of these diodes to effectively not be there until the voltage goes above the safe level, which I said 20 volts, and then it'll conduct it to negative. So there are ways of getting rid of it, but it definitely wants to be gotten rid of.
So another practical application question. So you go into an organ that has diodes all over it and you put it in a solid state system. Do you have to do anything about that?
Maybe. 50-50, Rick. I was in this very same movie with a Wix organ that had been transplanted several times, and in its final incarnation it was put in a very, very, very nice freestanding case with no room inside. And it had been built with the Wix solid state system, which many of you may know consisted of an aluminum panel with a bunch of transistors. It looked like this guy. And the transistor sent out positive, and it either went through a diode on their massive pin board that you plug the cables from the chest in with cotter pins. Have you guys seen these? Yeah, it's very interesting. And on the back side of the socket where you plug in the cotter pin, there's a diode. So that works for the straight ranks, and then they have one of the really ugly Wix Now, are there any Wix people here? Really, really ugly magnet with all the wires. Relay magnet with all the wires put together to break the ground. For unified stops, they had these switches with a rocking wooden bar in the center, which had, in their initial incarnation, a metal, like a phonograph needle, sharp on both ends. And when it was on, it connected this leaf to this leaf. So it said, we'll just drill it out and we'll put the diodes in there and let their leads do not such a good job of touching. So, in this particular organ, I was hired to put in a solid-state relay. This relay had negative outputs. I looked at this organ and I knew there were all these little glass diodes on every magnet. And in their wisdom, the way Wix made it so that to get into the chest you have to take the pipes off and lift up the toe board. This would have been, I'd still be working on this job if I had to do that. So I made a diode blaster. This is great fun. It was a capacitor this big around and that tall that I charged up to 90 or 100 volts DC. And then I had this cable with all these cotter pins dangling and wanting to break off. And I get it lined up and I close my It's the most satisfying thing in the world because I knew somewhere in the bowels of that Wix organ and the glass broke.
We just encountered something like that. We
Yeah.
had to remove 2 diodes from each magnet.
Uh-huh.
And two, because it was, some of the ranks were switched off through the ground.
Mm-hmm.
Well, that's not a very good picture. Anyways, so there was a lead going to the common bus bar, and there was a diode going between the poles of the DE magnets.
Uh-huh.
And the system we use, we have to do that, but if we had known we can just charge them and make them explode, we would.
However, the metal Borden chest had diodes that looked more like this one. They weren't the little glass exploding type.
Yeah, and then we didn't have those at all.
But there were only a couple dozen of those to cut. So anyway, it was great fun. And you have to be careful of the polarity.
Because the point is, if you don't get rid of them, it's bad for the solid
It's
state
bad.
system.
It's a direct short.
Yes.
Right.
You might as well be putting a screwdriver across the magnet and play the note. You're dying to say something.
I know, I wish we knew this, that would have been so fun, we just did.
Sometimes you'll
Oh,
encounter sometimes duplex magnets, which are like this. They have 2 coils. Let's say it's a direct electric like this. I can say direct electric because there are no Wix people here. It has 2 terminals and 1 common ground. So there is 1 coil that's wound between this terminal and the ground, and between the other and the ground. The reason that was done, in fact, I've seen Aeolian Skinner magnets this way, the brown Altron magnets. If they want to play a magnet from 2 different sources, let's say it's a big reed, and they want to play it from the positive and the great through a 61-note switch from each. One switch can be wired to one terminal on the magnet and the other to the other. And it's like they don't know each other exists because they're isolated. And you could do the same thing now with 1 coil and a pair of diodes, but this is pre-diode days. DACD. We've still got time to kill. Please. Right.
And speaking of magnetism, that device that you had passed around attached to the huge copper plate was a very early magnetic core memory system.
What's your favorite food?
Steak.
Okay. It is. Where is that thing now? Would someone hold it up? This is, it's called core memory. I remember when I was in college, kids studying computer programming would have to type all their programs on punched cards and put them in a box. And they would take it across the computing center and they'd dump it to core. It was, it sounded like real magic. What that consists of is hundreds and hundreds of little donuts, little ferrite beads, through which a couple of wires pass. And the little ferrite donut can be magnetized in one direction or in the other. And so in the combination action, it's one bit. Each bead is one bit. And that is either on or off. That corresponds to whether that stop is set on or off on this piston. And this came out of a 4-manual Rieger organ at the Unitarian Church in Washington, D.C. A very, very advanced organ for its time. Had brushed aluminum stop jams with light up push buttons. Actually, they were very sexy. They were square black buttons, and the engraving was done so that the engraving lit up when the light bulb lit up, and wasn't burned out. Anyway, it had 40 general pistons, and they'd spilled off from the key slips onto the right jam, which Herr von Glottergutz was very proud of at the time, but the reason I got involved was because they wanted multi-level capture system. And I couldn't bear to throw that thing away. It probably still got somebody's pistons on it. The other, any questions on the other things that were passed around? There are two Hall effect devices there. The Walker swell shoe has a moving magnet which approaches or recedes from a Hall effect transistor. A Hall effect transistor is like an ordinary transistor, except it is turned on in the presence of a magnetic field. So on the shoe, there's a little magnet, and as you open the shoe, it gets closer to the Hall effect transistor, which switches on more and more. The output of that shoe is 0 to 5 volts. So when the shoe is closed, the magnet is far away, it's at 0. And as you open the shoe, the voltage rises to about 5 volts. That looks a whole lot like what a potentiometer does if you fit it to an expression shoe. Have some of you guys done that? Mm-hmm. Yeah. Organ Supply makes a very neat swell motor that has an arm like this. And if you wire it up in the straightforward way, there are 16 input terminals, and you put it to a contact roller with 16 stages. 16 used to be the Cadillac of expression shoes. But the man who designed that was very, very clever, and he did it in such a way that if you energize the 16 input pins in various combinations, you can get up to 64 stages out of the engine, and then it becomes very smooth. And that's done by using gray code. Gray code is something invented by a guy named Gray who worked for Bell Labs. It's sort of like binary counting, but the thing that's clever about it is that from one stage to the next, only one bit changes from on to off, so that you don't have a whole bunch of things changing that might confuse the circuit. So Organ Supply sells linear potentiometers that are like a fat, well, like a pen with a rod going in them. It's just a potentiometer like this. Klon still makes a pedal that has a rack and a gear that turns a potentiometer most of the time. Organ Supply makes a neat little analog to digital converting card, so you can hook up one of their linear potentiometers, a Klon potentiometer, or the Walker shoe directly. And it has some switches. You can select what you want it to output, and you can have it output gray code to their swell engine. And it's really cool. It takes it to a whole new level. The Laukov swell engine, which is a big thing with a rod that does this, is designed to accept gray code. That's all it looks at. So the multiplex system that I'm most familiar with is the one from Solid State, and they have analog input modules that can be used to connect a pot or the string pot. Did you all play with the string pot? Isn't that the coolest thing? I keep one under my bed. You connect the pot to this analog input module on the multiplex system, and it converts the variable voltage from the pot, or the 0 to 5 volts from the walker shoe, into digital signals. It passes it to the organ, and then it can output it either as 16 separate stages for a wiffle tree motor or whatever, or gray code in various bit widths. Yeah. So yeah, that, and the walker shoe, he also makes modules that can plug into it, which will convert that 0 to 5 volts into 16 outputs. If you have to drive an accordion or a wiffle tree motor from it. Anyway, it's very nice. I'm not selling Walker stuff. That can be a whole philosophical discussion. But as products go, every once in a while I see something that's really, really cool. And that's part of the joy in visiting other people's shops. And when people come to visit at my place, I like to wheel out the cool stuff.
Yeah.
The meters, we're supposed to talk about meters. We passed around a few analog meters. The big heavy one dates from a period when things were made beautifully. Whether it was a tower clock that nobody ever saw, or a woodworking lathe or anything, it was just beautiful casting, lovely painting, gold pen striping, just because it's beautiful. Well, that meter was far more beautiful than it needed to be. And if you go into a Frankensteinian laboratory, you'll see lots of them, or like that marvelous science fiction movie where the Krell had an infinite power source and there were all these meters and they would light up. Analog meters, you don't see them too much anymore. They've pretty much been displaced by digital meters, which are very nice and small and compact and cheap, but sometimes they tell us way too much information, like decimal point 0056 volts, and you get paranoid. It doesn't mean anything. You know, a tenth of a volt will be enough for most of us. The other thing is that digital meters are not particularly useful for watching voltage that moves. For example, I cited the example of a big rectifier going through a small cable to a big organ. If you put the digital meter on the organ when no current is flowing, it will probably say 14 volts. As you play the organ, it moves stops on and off, that voltage is going to sink. And the digital meter is a sampler. It takes it, it measures here, it measures here, it measures here, it measures here. But it does it in a fairly slow way, so the numbers are changing, but they don't give you any useful information. What's much more useful in that case is a light bulb. And on the table back there, there's a simple little light bulb with a wire. That's the single most useful thing in my toolkit. Because you can look at it and say, okay, now push something, ooh, there's a problem. An analog meter in the same way will show that. You'll be able to see because the needle moves quite quickly. So digital meters have not completely displaced analog meters. And also if you're trying to measure things like the leakage voltage on an old rectifier, how much AC is coming out, depending on the digital meter, it could give you useless or downright wrong information.
And an analog won't measure that either, the AC content.
It depends on the meter, yes it
Okay.
can. Well, it has a bridge rectifier in it, that's how it measures DC. See, now you don't have to take that lovely meter back there apart. The meter, like the one on the board here, is a DC device. And so to measure AC, there has to be in there a bridge rectifier, which, yeah. You said, yeah? Is that it?
I think you had mentioned, if you had time towards the end, you wanted to mention something about the little wooden piston.
Oh, yeah.
With the,
Yeah, there are two of them there. There's one from Morgan Supply, and there's one from Harris. There's one right up there, and there's another one with one right up the right. use thousands of Harris thumb pistons. It's a very elegant product. He basically copied the Skinner and Aeolian Skinner contact model, which is 2 wires in these slots. And when you push the piston, there's a crossbar that 2 wires, crossbar shorts them. One of the wires is connected to plus and the other to the combination action. And when you push the piston, you do this. Now, that is 2 switches in series. Current has to go from plus through here and from the bar through there to do something, which, although David gold plates all this, it's still not enough. There are 2 problems that happen. One is called contact bounce, and that is where, and if you push the piston and kind of mash it like this, and look at that bar, it's like this. So the contact will go on, off, on, off, on, off a number of times, which, if it's just doing general 1, is no problem. You don't know it's doing that. What you don't know can't hurt you. If, however, it's working a reversible, like a sforzando, and surely many of you have seen this, especially on Grattio toll pistons, it goes on, off, on, off. And usually, it's like it has a 50-50 chance that's wrong most of the time. And so contact bounce is a problem. Also, they have tended to break. The little wires went through holes here and were secured by a block of maple. And they would bend at 90 degrees there. There was also a loop in the metal, which is where it was supposed to spring. But like fuses, like transistors that blow to protect their fuses, the contact would break at the 90-degree bend to protect the loop. So enough people complain that David redesigned the contacts, and they're really not much better. There's an organ builder in Wisconsin who has a client by the name of Arpad Marani. He's an Eastern European guy, was a developer for Intel, the chip people. And he bought the 4-manual Casavant Brunsuma tracker from Princeton and moved it out to Fond du Lac, where he lives, and he bought a defunct Roman Catholic church with a marvelous sanctuary. Built a gallery and hired Ron Wall, the organ builder in Appleton, to reconfigure and assemble this organ. And Ron is one of those people who leans on me for advice about electronic stuff, and he asked me if I would send samples of thumb and toe pistons to Arpad. So I sent him this, which was then like from Harris, and he got a Laukov toe piston from Wall, and he looked at it and he said, "It's terrible." No, he said, "It's really, really awful." And he's absolutely right. In industrial terms, that switch is awful. So he made this little circuit board, which has a Hall effect transistor on it, and you simply drill out the rod, the brass rod to which this is screwed, and put a tiny rare earth magnet in there, and as it passes by, it turns it on and off. And I said, that's really great. Can I buy some?" Well, he hadn't quite thought of that, but yeah, I guess you could order a few hundred more. So he gets them made in Malaysia. They cost about $9 or $10 a piece. I approached David Harris to see if he might like to offer this as an alternative to the metallic contacts. Well, he's sort of winding down. He doesn't want to do much R&D anymore. It's too much of a bother. So I talked to Brian Tim and said, "Oh, Organ Supply would be happy to do that." So they make very much the same sort of unit as the Harris, based on the Skinner version, with contacts that are even worse than Harris's because they travel more and they bounce more. But they are willing to supply their piston rails with the Hall effect sensor. And I assure you I could put the magnet on there, the battery on there, and it would work. Plus it makes them feel good because there are no contacts to bash into.
And that's exactly what it would look like?
Yeah, here.
So this, anyone here ever know anything about Organ Supply? Anybody at all? So the ones where they have a PC board, is that a different system than this Hall effect?
Yes, completely different.
Okay.
This is a great system, but because it has some depth, you can't use it on keyboards where the front rail pins are too close to the front,
Right.
or you saw them away, and that's really bad. I had to recycle a 4-manual set of very nice ivory molar keyboards, and the front rail pins were too close to allow this, even if you run it over the saw and get rid of everything you can.
Mm-hmm.
So in that case, I used the OSI PCB-based ones because they're shallower.
Mm-hmm.
They're not as elegant, but you know, they have their application. And Walker Technical Company makes a very nice drill a hole, shove it in thumb piston that has a Hall effect sensor, and also a light emitting diode inside if you like your pistons to glow. That's a cut above the Klon one. Reasoner used to have something like that too, and they're all just horrible. You know, why can't someone make a thumb piston unit where you can drill a hole and shove it in and feel good about it, and it would work? So I think the Walker one comes closer, certainly closer than the Klon one. But not,
These
not as nice
definitely
as
have a
that.
nice feel.
Yeah, of course they do. Is that it? Bon appetit.
We're good. So, yes, thanks, Skip.